Okay, so I'm going to talk about reinforcement learning, but provable reinforcement learning in feature space. So to begin with, we all know, we are here because reinforcement learning, RL, has been super successful empirically. And with all these amazing advances on solving problems that were not previously solvable. But I want to mention that RL is still not working at all when we have limited data or limited ability for doing trials or doing experiments. So if we think about Atari games or Minecraft, so really the game is there and our RL algorithm can generate as many data points as possible. But if we think about problems, for example, in clinical decision makings, so we really do not have an infinite generator of data. Or we can even think about problems in science if we want to understand how single cell evolves in its state space. So really, every single experiment may take a few months. Or if we want to consider how to optimize a drug treatment, and if we want to do clinical trial, then one single data point could be a human being. So in those regimes, I don't think people are trusting RL at the moment because we do not know how RL performs with limited data. That's why we need statistics. Okay, so let's consider two very basic questions which are typical in statistical machine learning theory. So the first one would be like, okay, say that I want to get a good policy, maybe 90% or 99%. And then how many data points do I need? So this question is very simple to answer if I'm asking it for regression. If I want to get an absolute optimal linear predictor, how many data points do we need? We know this answer very well and sharply. But we actually didn't know this answer for reinforcement learning. And a related and actually harder problem is, so how much regret do we have to pay when we do learning on the fly? And what is the minimal regret one has to pay? Okay, so those are the theoretical questions we try to study. And so just to familiarize you guys with my notations. So let's look at a very unstructured basic model first. Let's say that we just look at tabular Markov decision process. So we have a finite set of discrete states. So each state is unique. I don't know anything about their relations. And I know that there is an underlying transition probability law, which I do not know, but there is such a transition law. And also there is a reward function, which is a mapping of state action to a number. And we might know or we might not know the reward function. Okay, and this is a perfect optimization problem. So we want to find a policy to maximize the expectation of cumulative return. And we call this tabular MDP because so every state is just one single state and it has little connection to other states that we know of. So purely unstructured, that's tabular MDP. So what do we know about tabular MDP? So those are the theoretical sample complexity upper bounds that were achieved through a line of developments in pure learning algorithms. So if we look at this, so S is the total number of states, A is the total number of actions. And if you look at all these developments, actually it has been 20 years. So beginning with very basic pure learning. So we get something like 1 minus gamma to the 7. Okay, this is polynomial. Polynomial is good if we talk about complexity theory. But 7 is a big number. So I think in our most up-to-date result, which is this one, we get to the dependence to 3. Okay, so why do we care about? Because it's already polynomial, right? And now if we consider a long-time planning problem, say that we take gamma to be 0.99, meaning that roughly the game has 100 time steps. Then this improvement is 10 to the 8. So that's a fairly significant improvement, at least theoretically. And now is this optimal? So this is actually optimal under the generative model assumption. So suppose that we are working with this class of problems where we have a perfect simulator of the game. So a generative model that allows us to simulate transitions from any initial state and action pair. So in this setting, actually it was proved by a bunch of folks that the information theoretical limit for learning an absolute optimal policy with probability, I would say more than 2/3. In this case, we need to have at least this many sample transitions. And we could recently reach the lower bound, which means that, and actually, so there is an algorithm that reaches this lower bound, which is a very complicated algorithm based on randomized linear algebra and variance reduction. But I think the key message is, at least for this basic theoretical question, now the gap is closed, and we know sharply what is the limit, and we also know that, yes, we can achieve the limit. But however, so those results, although there is an algorithm, but the algorithm is not practical at all, basically because who cares about tabular MDP? I got this question a lot, right? Who cares about tabular MDP? So apparently, our state space is too large. And so the number of states is definitely exponential with respect to the dimension of the state value space. And if we look at the number of policies, even the logarithm of the policy space is the log of policy space is exponential in dimension. So the tabular results are good theoretically, but so what? Okay, so I want to encourage you to think of with me about, so what is really controlling the dimensionality of Bellman equation? So I'm writing up here an average, even a horizon undiscounted Bellman equation, because it's actually simple. Okay, so really, if we look at the Bellman equation, we either have a large system of nonlinear equations, or in the continuous case, we have an infinite dimensional system of equations that we want to solve. And we don't really know the parameters, the coefficients in the equation, so that's the problem. So another way to look at this is Bellman equation actually has an equivalent linear programming formulation, which is an infinite dimensional linear program. Okay. And we can write Bellman equation as an equivalent saddle point problem. So I think this is interesting in a way that we have a minimax duality between value functions and a long-term probability measure over state action pairs. So we have duality between value function and a probability distribution. And that probability distribution actually contains the the conditional distribution for peaking actions. So that probability distribution captures the policy. So we have duality between value and policy. Okay, again, this is going to be a huge or potentially infinite dimensional problem. But now it really looks like regression in some way. In regression, we want to minimize over a function space. In this case, we have min-max over value function space and distributional space. Okay, so how can we think about dimension reduction from here? Okay, let's try to, again, borrow ideas from just regression. I want to estimate a function, which is the optimal policy and the corresponding distribution. And let's say that can we have some feature functions where I have a function class. Let's begin with linear models for simplicity. So actually, if I have a state feature map, so every raw state can be mapped to a number of feature values. So in this case, actually, we can already solve many, I would say, simple games pretty well. So actually, it was, I think, 23 years ago, one can already solve Tetris using only 22 features to achieve near human performance. So it's really not that hard. Because Tetris is a simple game. This is the first game ever, so it's not very surprising. And the features will be just like the height of the wall and the number of holes on the top level and things like that. They're just handcrafted features. Okay. And so, the way it works is, okay, we want to parameterize high dimensional value functions. And let's just look at a very simple linear model. I'm going to, let's say that we parameterize value function using a linear combination of the features. And so what is this parameterization really happening in reinforcement learning? Okay. Again, let's circle back to Bellman equation. So I explained that the Bellman equation is equivalent to an infinite dimensional LP, linear program, which is equivalent to a minimax problem over function spaces. So when we use features, or when we use maybe other function approximators or neural networks, so essentially we're solving this minimax problems over space of functions, instead over spaces of function classes or over parameterizations. And in the case, if we just use linear models, we can actually reduce this to a finite dimensional, very simple minimax problem. Does it make sense? So we can parameterize both the space of value functions and the space of ergodic distributions, which also contains the optimal policy we want to look for. Okay. So we proposed actually a primordial policy gradient method, I call it policy pi-learning, to solve the minimax problem using features. So we already have a low-dimensional minimax problem, and the algorithm is super simple. So every time we have a sample of state control, state transition triplet, and based on the one single sample, we can compute unbiased estimate of partial derivatives of the Lagrangian function. And then we can do a primal and due update using the correct Bellman divergence for projection. Okay, and this is the actual algorithm, which is also very short. Okay, and we can prove very strong theory for this type of algorithm. So one can show that the sample complexity is linear in the number of parameters, which is very well expected, right? That's what happens in linear regression. Okay. So that's one idea. So next, let's think about, okay, so, what if I do not have this hypothetical generative model? What if we move closer to the real world? We have to learn to control on the fly. Okay. So in the generative model, the theoretical results can be strong because there is an implicit assumption that this simulator allows us to visit the entire state space if we want to. But in practice, we want to do RL for a computer game, usually starting from a fixed state or a random or a fixed distribution of initial states. We cannot be taken anywhere in the state space, although we want to do so. Okay, so now we want to consider just the real online RL. So in this case, the learning algorithm has to start and try to exploit by acting in the real world. And its ability of exploration is limited by the game itself. And it's not possible to visit every corner of the state space. Okay. So then theoretically, what do we care about? So I assume everyone is familiar with the bandit theory. So similarly, in this case, we care about the regret for episodic or reinforcement learning. So one episode is just one trial when we use RL to control this game. So we want to calculate the regret across the episodes that have been visited so far. And we compare the ideal optimal performance with the actual performance. And that's the regret. So if we think about this and compare episodic RL with just bandit, then we realize that bandit is actually a very simple problem. So bandit is really like an RL problem with one single state. So every time we make an action, then the game resets to the beginning. But if we do online learning, then basically one single decision at the very beginning may lead to long-term negative effect, which is unpleasant. And theoretically, if we want to analyze what's happening there, we actually run into a huge problem. All the data, all the variables we're dealing with are dependent. So that makes proof pretty hard. And again, we want to understand the exploration trade-off, which is always the central problem in learning theory. And so for RL was, for example, in the tabular case and in the case of linear control and the indeterministic case, actually there have been lots of pioneering works and milestones, which I don't have time to go through today. So I'll show you how to do RL with provable regret in the feature space. So let's say that we already have good features. The feature map can be already a neural network or can be hand-coded features, which are something we already have that we believe in. So for each state and action, I'm going to take them as a pair. So I'm going to look at the feature for this state and action. If they have separate features, meaning that we just take their product. So I'm going to get a longer vector. And also I have state-only feature. So we're going to make, for theoretical purpose, we're going to make an assumption that, which is very similar to an assumption in just linear regression. I'm going to assume that whatever unknown about this process can be represented using the features. And in particular, I might have an unknown transition kernel or transition operator. I'm going to assume that it can be fully embedded using the feature space. And this assumption is actually equivalent to using linear model for value function approximation with zero error. Okay, so let's see what we can do here. Okay, so the algorithm is not very hard. So first we're going to map all the state, action, state, transition triplet into vectors, into feature vectors. Okay, so based on that, so suppose that we just do model predictive control, we just do regression. So based on those, we can already find a low dimensional representation for estimating the entire transition kernel. Okay, but that's apparently not good enough because if we believe in our estimate greedily, we won't be able to explore. And this is basically the first thing to know about online exploration. So we also borrow ideas from Linear Bandit. So the way it works is, okay, we still want to do Q-learning, but we're going to do it in a very well controlled way. So we're going to have basically a confidence ball around the model, the transition model that we are trying to estimate. And the confidence ball actually have a finite dimensional representation, so it can actually be computed. And every time we want to do Q-learning updates, we're going to do this update by being optimistic. Being optimistic means that I'm going to find probably the best possible model in my confidence ball to do the updates, to make sure that my Q function, Q value estimates are actually higher than their actual values. So this is to encourage exploration. So basically state actions with higher uncertainty should be tried more often because they are going to have higher Q values. And I'm going to use those Q values to control the next episode. So this is a typical upper confidence Q-learning method, but in the feature space. Okay, so we can prove something, of course. So one thing we can prove is, well, the regret depends linearly on the number of features. And it's also optimal in T, in square root of T. It's not optimal in H yet, but this is the first, I would say, polynomial regret for RL in feature space. And actually the method can be kernelized to work with any priorly given kernel function over state action space. And in the kernel space, the regret depends on the RKHS norm of the unknown model and the notion of effective dimension of the kernel space. Okay. So apparently using features and linear models for RL is very questionable. And we all know that. So I think the nice thing about it is when we are talking about linear model class, it is the first function class to consider whenever we want to understand the mathematics and geometry of the problem. So it's natural. And actually when we do the analysis, when we try to understand the regret, we realize that there is deep connection to just regression. So we're actually connecting, I would say, basic statistical regression 101 with reinforcement learning. So that's interesting in a theoretical way. And there's not many parameters to tune because the model is so simple. And there are a serious issue as well. So it is well known that if the features we use for value function approximations are not good, which is usually the case, And in this case, the policies the algorithm, any algorithm can behave very stringently. So the algorithm might oscillate. And this phenomenon was already noted in a book 12 years ago, in a control book by Dimitri Bersikas. And similar oscillating performance is also noted, over and over and over in, deep Q networks or other related algorithms, as long as the feature maps are not perfect. And apparently, linear models are not as rich as nonlinear models, but there are a lot of connections and a lot of open questions to be further understood. So the next question I want to start working on is, I want to understand, okay, so what if we don't have the good features to begin with? Is there any way, or at least is there any principle to start looking for good features to make linear model work? Okay, and so this is a domain called, I would say, state representation learning or state abstraction learning, and there have been, again, a lot of prior works here. And I try to understand it, again, in connection to statistical theory. Okay, so what should be good features for states? Recall that we are going to use features to parameterize value functions. So let's just look at the linear algebra that defines value functions. So V is a value function which can be infinite dimensional. And here, by P, I mean the transition operator, which can, again, be infinite dimensional. Okay. So apparently, if you look at this, V is defined by reward function R little r and P jointly. And it's actually mostly about P rather than R. So it's mostly about the environment, the transition model of the problem we want to solve. So now suppose that in a setting where I might be observing complicated raw states, but maybe the underlying transition model has some low dimensional structure. For example, if P happens to have such an decomposition, and then it's very easy to see that the value function and the do variable, which is the ergodic measure, they happen to lie in the space spanned by, I would say, left and right singular functions of the transition operator. Okay, so now the question is, okay, can we look for the singular space of the transition model directly because they are naturally good feature functions for the states? Okay, so more formally, so consider a problem like we are given a state trajectory and each x is a raw state. So in the tabular case, it's just a discrete state. In the more general case, x can be an image, or x can be a vector, or a vector of prices, for example, in trading. Okay, so let's say that I want to be able to approximate this complicated transition operator. I want to approximate its leading spectrum. So U and V are, or let's consider them as like, for example, singular functions, but they are functions. So can we estimate a state embedding? Say that I want to find a feature map per psi that maps each x into a vector. And now if you look at this, we want to be able to make sure that the span of the feature vectors, feature functions, are approximately equal to the span of the ideal left singular functions. So can we do that? So we can do that sometimes. So this is our recent paper to appear at NeWIFS this year. And we figure out a way to do kernelized state embedding, but not for RL yet, just for time series. Okay, so our input are x1, x2, so we have a time series data, and each xt is a multi-dimensional vector. It could be high dimensional. But I already have a kernel space, which already tells me something about the topology of the problem I'm working on. Okay. And recall that we're trying to do high dimensional, not high dimensional, we're trying to do non-parametric function approximation. So I'm going to do it in a way that we try to open up the kernel space. Remember that a kernel space is an infinite dimensional space. So we try to open it up and use randomized decomposition to approximate it in a large finite space. Does that make sense? Okay. So once we do that, we can try to estimate, I would say, a projection of the actual infinite dimensional transition kernel on the finite space spanned by random features. So at least we have something that is finite. And the next thing is we try to downsize our estimator by doing something like spectral approximation or low rank approximation or other reduced order approximation methods. And in the end, really what we look for is we want to find a mapping that starts with the raw state. And eventually I get something which has a small dimension. Okay, so what is this doing? So a little bit theory. So this method is inspired by studies on molecular dynamics and chemical physics. So this kind of approach we use to do dimension reduction for complicated or large-scale scientific simulation. So the idea is, so really what we want to do is we want to preserve a notion of diffusion distance between states. So say that I have two states x and y. We quantify their distance by using the difference between their outgoing transition distributions. So that's the diffusion distance in the original high dimensional space. So we can show that the kernel's embedding method actually preserves the diffusion distance, which was in distributional spaces, now in finite spaces. We can preserve diffusion distance with, I would say, small error. So n doesn't have to be very large to make this small. Okay. And we have a bunch of other theorems which are too boring to present here. Okay. So just to show you one example to have something other than equations. So we actually tested the state embedding approach on a very simple Atari game, which is called Demon Attack. So the game works by we try to move horizontally this cannon and shoot some demons on top, and the demons are going to appear randomly. Okay. So this is the t-SNE plot to visualize the topology of raw states of Demon Attack. So t-SNE plot is a plot that preserves distances, or maybe in this case just Euclidean distances in their raw data form. And then we apply the embedding approach. So hopefully the embedding approach should be able to tell me something more about the dynamics. So this is the t-SNE plot after embedding. So first we can see that, okay, so apparently there should be more structures. If you're familiar with t-SNE plot, you will know that the one on the left basically says that there's a little structure, but the one on the right is actually more cluster and there's more structure. So we identified a few pair of states. So for example, like those two circles, they are two different states, but we identify them because they are very close after embedding, but they are far apart before embedding, meaning that in their raw images, they should look dissimilar. Okay. So we try to identify some of the pairs and try to understand what's going on. So it's quite interesting. So we have three pairs that are not similar in their raw data form, but are considered similar after embedding. So really, so if you understand this game, so for example, in the two circles, in both states, the laser which is this purple dashed line, the laser is about to get to the target. So this is a state prior to scoring. And also, both cannons actually are moving to the left. And this is also interesting. For example, in this case, this cannon just shot. It's not getting anything. And this cannon is moving from left to center. And this cannon, again, is missing its target, but it's moving from right to center. So basically, state embedding can help us to identify states that do not appear similar, but they are actually might have similar future dynamics. So that's why we want to do state embedding. And getting back to the point, the distance preservation property actually shows that the estimated feature map is approximately spanning the left spectrum of the transition kernel. So at the same time, they should be ideal state features. Okay, so just to acknowledge my collaborators and students, thank you very much.